Thorsten Enßlin to you. We invited him because there is a lot of interest in the cosmic microwave background, especially in our European satellite Planck. He's one of the leading figures of Planck in Munich or Garching. Thorsten got his PhD in the last year of last century, 1999, in Bonn. Peter Biermann worked at that time on regular and all kinds of things which are much smaller than the cosmic microwave background. And then he moved to Toronto and came back to Germany, going back going to MBA in Garching sometimes around 2003. Anyway, in 2003 then he was convinced by Matthias Bartelmann, who moved to Heidelberg at that stage, that he should take over the Planck part in Garching. And so since then, since 11 years, he has been working on Planck and will hopefully present some of the most exciting results from Planck.
Thank you. Thank you for the kind invitation. Noise level is okay? I hope so. Our universe, cosmological results of the Planck mission. So I will try to give you an overview of the different results the Planck mission has obtained about, well, different periods of our universe which are accessible by the Planck data. And here you see two maps, and at the end of my talks, you understand a bit better what the cosmological relevance and astrophysical relevance of these structures are. But let me start simply. If you look to the night sky, then you see a lot of stars and dust and the Milky Way. And so that is close to what our eye sees as the near-infrared. A common perspective on the Milky Way. However, if we go into the microwave regime and adapt our eyes to these wavelengths, the sky should look roughly like this. Extremely homogeneous. So the light coming from all directions is basically the same. And this tells us that the universe appears to be isotropic, homogeneous, and, as we will learn in this talk, also to be flat. And this has caused some concerns among cosmologists, because the photon which comes from that direction and which traveled through the universe for a long time tells us that the universe looks in this direction exactly like the universe in that direction. Also, these two locations didn't seem to have any chance to exchange information, because information exchange goes with the speed of light, and the light is still on its way from over there to over there. It has a long way to go. One solution to this problem was, of course, we all know the universe is expanding, and so it was smaller in the beginning. And one might argue, well, okay, if it was smaller, then this exchange of information could have happened in the very beginning, and then it expanded and it looks homogeneous today. However, even if you go and solve the Friedmann equation and check for this, with a standard assumption of what we believe are the constituents of the universe, this didn't happen. So even everything was very nearby in the beginning, there was not enough time to send a signal from the location over there, to the location over there. The solution, the proposed solution to that was a concept of inflation, namely that before the period when the universe expanded as it does today and extrapolated backwards, there was a time when it expanded very rapidly, so that initially these 2 points were so close together that they could exchange information, and then they were moved away to so large distances that from our present perspective it appears that they seem to be disconnected. And I'm telling you this because with the Planck mission we are starting to test this concept of inflation. And we are doing this by investigating the microwave regime, where the universe looks mostly homogeneous, but if we subtract this homogeneous screen from the data, then we start to see more structure. So we see a microwave emission of our own Milky Way here in red, and we see a large dipolar modulation with a large temperature increasement of this radiation field by a thousandth degree in this direction and a decrement in this direction. So this dipolar structure we understand very well. It comes from the fact that the Earth moves around the Sun around the Milky Way is falling into the direction of the great attractor, and therefore we see a Doppler boosting in the sea of cosmic microwave background photons coming from all directions. We can subtract this effect from the data, and what appears then are structures on the level of 10 to minus 4 and 10 to minus 3. Variation in the temperature of this photon field, which you can see here above and below the galactic plane, which shines through. These structures tell us from the earliest time of the universe. They tell us from epoch when the complete visible universe we see today were concentrated in a volume as small as a grapefruit. And if this inflation paradigm is correct, then all these structures were seeded and produced at times when the universe was much smaller, even as small as a fraction of a nucleus. And now I ask just to believe this. Well, of course you shouldn't. You should question things, and one way to question things is to do experiments. The experiment which we did was to launch the Planck satellite. We put it to the second Lagrange point of the Earth-Sun system, where it rotated with its axis pointing towards Earth and Sun, which are in the same direction from there. The instrument is looking to the side, and therefore scanning the sky in circles, as illustrated in this ESA propaganda movie. So it scans the same circle for 60 times roughly, and then the axis is displaced. And in the course of the year, the axis of the satellite has always to point towards Earth and Sun in order that the instruments are firmly shielded, and therefore the scanning strategy covers within half a year the full sky, and we can download the data from the satellite and put it together and produce an all sky map of the universe. And the most prominent thing you see is the Milky Way, which we also see in our data. So that is one of our biggest enemies as a cosmologist and our biggest friend as an astrophysicist. And above and below the Milky Way, we see tiny structures in the temperature distribution of the cosmic microwave background. And we believe these tiny structures were seeded during the epoch of inflation by quantum processes. And these tiny structures are imprinted in this radiation field. These tiny structures are believed to be the source of all the structures we see in the universe today. I was urged, since I'm here in Heidelberg, to explain you the structure of our universe. So here's the sun, right? And the Earth is the third planet around the sun. You asked me, right? I should tell your students how.
Could you say this again? I didn't get it.
Okay. Okay. So in the data we have from Planck, we are seeing effects even from the solar system, like zodiacal light. We see the Milky Way, of which we are part. The Milky Way is part of the large-scale structure. The large-scale structure is imprinted in the universe by the distribution of galaxies with its filaments and galaxy clusters. The microwave background photons, which fill the universe, are a remnant of the hot Big Bang. And since, if you look out, we look back in time, it comes back from very early epochs of the universe, when the universe was 380,000 years old. So this light traveled all the way to us, went through the different epochs of the universe, when the structures which form the galaxies were forming, and it seems to come from a surface where it was from an epoch when the universe had a transition from being intransparent to transparent. So the universe was smaller at earlier times, everything was more dense and hotter, and so if you go back sufficiently far in time, it was so hot that the universe was ionized, and so a fog of free electrons existed at these earlier times, which scattered the photons which were produced at the very beginning, which scattered the photons and prevented them from taking straight paths. At 380,000 years after the Big Bang, the universe became transparent because the electrons combined with the protons to neutral hydrogen, which is transparent. And so since then, they come in relatively straight lines towards us. And so we look back on the surface. The structures we see in the surface are imprinted by a number of physical processes which trace back to earlier epochs, and they might allow us to peek into this still hypothetical, or at least this hypothetical epoch of inflation when space should have expanded, and when we believe that quantum fluctuations seeded the structures which then are visible at later times. So with the data we get from Planck, we get information from all epochs. Directly we see this, but the light travels through the data universe and got effects imprinted there, and a physical process at earlier times produced these structures, and say, if our paradigm is correct, were seeded during inflation. So different epochs, and the universe was dominated by different energy and matter forms, and the fuel of inflation we just call inflaton, because we don't know what it is. We just assume that in the simplest version that there was a field in the universe which had a huge energy density, which did not fall when the universe expanded, and thereby, by the Hubble law, maintained a high rate of expansion. After inflation, the remaining energy momentum of the field was dissipated in particles and radiation. Everything was relativistic. Every species of basically all particles we know and can imagine should have been present. Once these particles became non-relativistic because the universe expanded and everything cooled down, they mostly annihilated and left radiation and neutrinos. So the universe was radiation dominated for a couple of thousand years until the expansion of the universe had diluted and de-energized the radiation field so much that dark matter became the dominant energy form of the universe. and we believe this happened until the relatively recent history of a few gigayears. And now the universe seems to be again dominated by something called dark energy, another mysterious energy form filling the space, which does not suffer from expansion as much as radiation or dark matter. Since I'm here in Heidelberg, I also should mention that modification of different scenarios exists and modification of the scenario exists. For example, there's the proposal that something like early dark energy existed, and the quantum of that is the veteran, as a field with reported quantum localization here in Heidelberg, so it must exist. We have seen at least one element of that. Just for the geometry, so imagine these are the galaxies, we sit in the middle. At the beginning of time, each location, even the room I'm sitting was filled with this CMB, with a photon field coming from the Big Bang. But the photons, which started here, are now at the other end of the universe. Basically, they're at all these locations where we see the photons from the microwave background coming now. So each location had photons, they were running in all directions, and some of them reach us today. And by geometric considerations, you can find that these should be in a spherical shell surrounding us. But when we look out, that's what we see. We don't see directly these large scattering surfaces with these tiny temperature fluctuations printed on that. We see a lot of galactic astrophysics in front of us. Namely dust emission, so dust grains of the Milky Way, which are heated up to roughly 30 K by the radiation field of our stars, and then re-emit in the microwave regime, and synchrotron emission by relativistic electrons spiraling in the galactic magnetic field. So how to get rid of this stuff? And what we did in Planck was to observe the sky at 9 different frequencies, from 30 gigahertz to 900 gigahertz, and here you see the all-sky maps. And what you see is that the synchrotron foreground is relatively strong at 30 gigahertz. It gets weaker if you go to 70 and 100 gigahertz. Here's a sweet spot, so we see a lot of the CMB fluctuations. They are all the same in all these maps. And then, at higher frequencies, dust emission becomes stronger and stronger and stronger. So why don't we observe only here? Well, because at these frequencies we see our contaminations relatively strong, and we can map it out and try to subtract it. In order to convince you that this is possible, let me show you a patch of the North ecliptic pole at 70 gigahertz in a color scale where the CMB fluctuations are kept with the same color scale when I change the frequency. So this is 70 gigahertz. Now I go to 100 gigahertz. You see, the CMB fluctuations stay roughly the same, and just the dust changes. Okay? So what we can do is we can subtract one map of the other, and we got rid of the CMB. Isn't that great? And we see all this beautiful dust and this beautiful free emission. Now, if we can get rid of the CMB, we might be able to do a different operation with this map and get rid of the dust. We might agree with that. And of course, this operation is a bit more complicated than just subtracting this map, because for that we have to know what is the detailed frequency, the spectra of the dust, which is the spectra of the free emission, and the spectra of the relativistic electrons, the synchron emission, and this is an empirical quantity which has to be measured, and therefore it's better to have many frequencies in order to determine these things and to mix the data from the mixture we have in the data. To demix the data. To illustrate this, the ESA produced this movie So in the data processing, after we've created the maps, we first identify the individual sources and subtract them. Then we identify with this falling spectrum the radio emission from the Milky Way and subtract it. What is left over is in the galactic plane dominated by dust emission, and spectra is roughly known. We subtract it, and what we get is a very nice cosmic microwave background, showing temperature variation around the 3 Kelvin of this radiation field of 10⁻⁵. Red means hotter areas, blue means colder areas, and in the next 10 minutes I want to walk you through a number of physical effects which imprint on these maps, which help you to read these maps, this map, just by looking at it. So the simplest physical effect which is imprinted here is effect of gravity on photons. I told you quantum fluctuations should have produced small structures. After inflation, these structures were imprinted in the matter distribution of the universe. There were denser regions, less denser regions. Gravity is only attracting, so the structure grew. The potential wells got deeper and deeper. The photons were trapped because they couldn't move far away due to the electrons which scattered them until 380,000 years after the Big Bang, when the universe got transparent. From that moment, photons came straight towards us. However, a photon which had started at the bottom of such a gravitational well had to move upwards and thereby suffer from gravitational redshifting. This removed some fraction of its energy, and therefore, if you see a large region in this map which is a bit colder than the environment, then this is probably an area where there was such a gravitational valley. You can see this area by eye. We did the Planck mission in order to map the microwave background with high resolution, so we can zoom into this map. And if you do this, you recognize that there's a characteristic size of this fluctuation. So you see patches of all scales, big ones, small ones, but patches with the size of 1 angular degree are relatively frequent. The physical effect behind that is illustrated here. So we had an enlargement in dark matter, overdensities which collapsed. The gravitational pull pulled on the baryonic fluid in the universe, the electrons and protons. They wanted to fall into this gravitational valence. However, the photon field, which wasn't dominate the energy density of the universe at this time, but which was still dominating the pressure, the photon field inhibited a contraction of the baryons because the photons were scattered with the electrons wanted to move together, the photons were compressed, got hotter, and the thing bounced back. And so we got oscillation in this fluid, and these are sound waves, sound oscillations. The sound waves which were triggered by the overdensity in dark matter could only propagate a certain distance, up to the time when the universe got transparent. The universe got transparent 400,000 years afterwards, so the speed of sound was 60% of the speed of light at this time, because everything was photon pressure dominated. So we can calculate, okay, sound wave travel time is half of that, 200,000 light years, and then the universe was expanding during that time, which helped a little bit and boosted this distance to 500,000 light years. Okay, so sound waves could travel 500,000 light years, not further. And 500,000 light years, seen from our present distance, is just 1 degree on sky. And that is the reason why we see patterns or structures of 1 degree size relatively prominent. Actually, in our analysis, the argumentation goes the other way around. We know these structures must be 500,000 light years at earlier time. We observe it to be 1 degree, and then we ask ourselves how far are we away from it in order that they look 1 degree, and translate this into the age of the universe, and that's how we measure the age of the universe to be roughly 14 billion years. Okay, the last effect I want to introduce you is the photon diffusion and recombination. So the transition of the plasma phase, electrons and protons separated into the neutral universe, took some time, and so the last scattering surface is not just a sharp surface, but is some fuzzy region, which is not that well defined, but it's like looking at a cloud. The shape of the surface of a cloud is not really sharply defined. And for that reason, structures which are below 5 arc minutes are washed out. It's stronger suppressed. And it's not an accident that the angular resolution of Planck is is 5 arc minutes, because at smaller scales there's less to see. There's still something to be seen, but there's less to be seen. Okay, so much about effects happening around large, the last scattering surface. And the photons still had to come towards us, and so they had to travel a journey, and a longer journey, and if I manage, I can show you a movie. That looks good. So imagine we can jump into the early universe and go into the time before the combination of electrons and protons. And here you see in red the protons, in green the electrons. As you know, electrons are green. And in blue, the photons. The photons get scattered at the electrons all the time. The universe expands, it gets colder. You see the colors get a little bit darker. And now electrons and protons have combined to neutral hydrogen, and the photons can travel in straight lines. Here we have one of them. And we look at it as going through the universe where stars start to emerge. You see the color of the photons changes. The universe expands, the photon gets stretched, and therefore the wavelengths of the photons also gets more greener. If it comes close to a mass concentration, like this galaxy cluster, it gets bent as gravitational lensing, yeah? And now it's entering a galaxy cluster, which is filled with ionized plasma again, and can get scattered at electrons, and thereby it gets a small photon shift. You might have seen the change in the color. That's the so-called Zeldovich effect. It can happen that photons enter galaxies, and in some galaxies, there are instruments which absorb them. And one of the instruments is close to Earth, and the inhabitants of Earth have then painted the received data back onto the sky in order to get an impression of these CB fluctuations and showed us. Okay. Thank you. This was done by NASA, this movie. Did I say anything funny? Are there questions? Okay. Oh, the wrong button. No, it's not good. It's funny, yeah. So, the photon parcels get bent by their passage to the large-scale structure, and this makes a CB pattern, which initially looks like this, to look like that. Okay? Back and forth. You see, it's a tremendous effect, but we can use this, because this is done by the large-scale structure of the universe, yeah? And we just have to compare these two images, then we see how things were shifted around and can reconstruct where all the matter is. The only problem with this approach is that we have only one of these two pictures. Nevertheless, from that image, we can reconstruct the matter distribution between us and this large scattering surface. How does this work? Well, if you go back and you look at the distribution of these spots, you see they are isotropic. Well, they are elongated, but statistically they are as often elongated in this direction than in this direction. Now, they are anisotropic. In certain regions, they are more elongated in one direction than in the others. You clearly see this. Anisotropic. Well, and even if you don't see it, we have algorithms which statistical algorithms which dig out these weak signals from the data and convert this into a map of the projected mass distribution in the universe. And here is such a map. It shows you roughly the mass distribution when the universe was 3 times smaller, so at redshift 1 or 2. White means enhancement of mass of masses at certain locations, and blue decreasements. The signal to noise in this map is not really great. So at any locations you can't be sure that it's really as the map shows, but statistically it's more true than false. And we can analyze these fluctuations. And the interesting thing is, these fluctuations we see here give us information about the matter distribution in the universe, which should, if our paradigm is correct, of structure formation, it shows us the same kind of fluctuations we observe in the cosmic microwave background, just as at later time. But we observe the same thing in a processed version a bit later, and by comparing that, we get information of how structure grew, and therefore how our universe evolved. Okay, how do we analyze the data? Now you understand many of the physical processes imprinted in this pattern, but how do we characterize them? Well, one can describe it in this way. We try to make a statistics of how strong patches of different sizes are excited, or mathematically we measure the 2-point correlation function of a temperature fluctuation at one location times the other location. And if the universe is really isotropic, then this statistics only depends on the 2 points. And this we convert into a so-called power spectrum, an angular power spectrum. So if you're familiar with spherical harmonics, that's just the spherical harmonic power spectrum of the map I'd shown you. For the others who are not familiar with that, we are still in Heidelberg. Here is the angular scale. Scale printed with large scales over here, small scales over there. And here is printed how strong the temperature, how strong patches are excited on this angular scale. And red is the data, and green is a theoretical curve fitted to the data. And in the fit, we have fitted 6 parameters about our universe. So we have fitted six numbers in order to explain 2,500, which is quite remarkable. Actually, yeah. What is of course very visible is that at 1 degree we have a peak, and this is this acoustic oscillation or sound waves I talked about, and they are also responsible for the sequence of peaks we have in the spectrum. On the smallest angular scales over here, the effect of focal diffusion I introduced to you is apparent by the suppression of power in this diagram. And on the largest angular scales, on the left-hand side, This plateau in the power spectrum is mostly, but not completely, due to the gravitational redshift effect of photons escaping from gravitational potential variations. So that is how we analyze the data, and we compare our theoretical prediction to the data and vary the parameters which enter this prediction, like the amount of dark matter, the amount of normal matter, the amount of dark energy, which all influence the expansion history of the universe. And for all these cases, we get a different power spectrum, and by varying the parameters, we see what is basically the best fit, and explore how much the data constrains these parameters. To visualize this, my group has produced the following movie, in which I take you on a tour through hypothetical universes which have properties which are very different from the one of ours. So we change the parameters of the universe and look how the CMB would look like in these universes. And in order to make this journey interesting, I'm using universes which are not consistent with the data, because all the universes which are consistent with the data, the CMB looks like that. That's the data. Okay, so here's the movie. And the parameters we change are flatness, so we are bending the universe, the amount of baryons, and you see the effect on the statistics of the fluctuations are quite dramatic if you change this parameter dramatically. So sometimes you get very large structures, sometimes it gets smaller, and sometimes it's like now it looks roughly like our universe. When we analyze the data, of course we do this in the computer, and on the basis of this power spectrum. Here's the power spectrum we published in 2013. And here's, the dots show the spectrum mode by mode. Actually, there's quite a large scatter around the theoretic model, but this has to be, because these fluctuations are generated by a Gaussian random process, and this thing has variance. And it's not always, well, if you use a die and you dice, you don't get a 3.5, because that's the average value, you get all kinds of numbers, but they scatter around the average number, so the scatter is correct. This was done with 2.5 years of the Planck data. Now we are going to release the full machine data shortly, and I can show you the 2014 or the 2014 results. That's how they look like. Not much changed. The most apparent change is that the amplitude, in particular you see it in the model, the amplitude is a big change because we found some problems with our previous calibration. But otherwise, all the features stayed at the same time. Some of the artifacts which were reported got a bit less worse. Some of the artifacts, so deviation from the theoretical model, which are a little bit larger than we would typically expect. Some of them stayed, but roughly our new analysis, except for this slight recalibration, is consistent with the previous one. What we also released, what we are also going to release now, is for the first time polarization data. So far I've shown you only temperature fluctuations, but the cosmic microwave background is also polarized. And here is the cross-correlation spectrum of the temperature fluctuation with the so-called E-mode polarization. You see the data? And the theoretical curve, which goes right through it. Here's the polarization correlating with itself. And again, excellent agreement of theory and data. What I find most impressive about this is not a fit. The theoretical curve are the curve calculated for the cosmological model, fixed with the temperature data only. So this is a test of the self-consistency of our cosmological scenario. This could have gone terribly wrong. But it tells us that the universe, at least on the scales we are probing it with the Planck, is roughly as we imagine. We can predict in detail, we have predicted in detail what these correlation functions should be and all these wiggles, and then we measured them, and they were like that. And if you remember how cosmology was a few decades ago, well, people measured the Hubble constant, it was either 50 or 100, but not in the middle. And now we are measuring the same thing in different ways, and we get a consistent answer. And that's impressive, to me at least. We can do similar analysis with the lensing. We can measure from this lensing map, also the signal to noise is bad. It's sufficient on the odd scales that we have now roughly 40 sigmas of lensing signal, and which allows us even to measure a spectrum of lensing. And here's a new spectrum, and that's the last spectrum, they're consistent, and some other data points. So we measure a lensing spectrum, and that's the prediction for it, given our cosmological model, and it fits. If you now go and look into the parameter space and ask, for example, only this lensing, how much does it constrain parameters? So here's a glimpse into the sigma 8, which is the amplitude of the fluctuations over omega m, which is the amount of matter, mostly dark matter, in the universe, in this plane. And the dots are the different allowed solution constrained by the lensing data only. Of course, these constraints are not very tight, but the interesting thing is if we look at the constraints we get from the temperature data, then it's this ellipse and it's consistent with the lensing. Maybe there's a little bit of pull on the 1 sigma level, but it's both data sets obtained very differently. One is the fluctuations on the last scattering surface, the other is the lensing effect onto them, tell us a consistent story. If we add polarization data, if you combine these two constraints, we can of course tighten our constraint because we have to fulfill a larger set of conditions. Okay, so this data set allows us precision measurement of cosmological parameters. So before Planck, we believed that the universe is 72.8% filled with dark energy. Now we think it's only 68.3%. So dark matter, there was a bit more dark matter, a bit more ordinary matter. These numbers changed on the percent level. The expansion rate of the universe seems to be a little bit lower than we assumed previously. The age of the universe, as a consequence of that, seems to be a bit older. So in short, by Planck, the universe became heavier, slower, and older. And the more senior people among us can understand this completely.
Is this 2013 or 2015?
Pardon?
Is this Planck 2013 or 2015?
This is 2013 actually. The 2014 values are here. So these are the main parameters we derived. Not all of them are completely independent because the main cosmological parameter is only 6. The most well-determined parameter is angular size of these parallel acoustic oscillations of about 1 degree with an uncertainty at the 4th digit behind. And if we add in the polarization data, it gets even better by more than 30%. And all the other parameters are now measured with precisions which one can sell as good precision parameter estimation as it should be in physical textbooks. So this cosmology is really turning into precision science. Should I go through this list? Okay, maybe I should say this is the amount of baryons. That's in terms of the critical density, which critical density means black universe. Cold dark matter, Hubble constant. The spectral index, which says how strong the fluctuations on large scales are excited with respect to the fluctuations on small scales. The most scale-independent value for this quantity would be 1, which on a logarithmic scale would mean equal amount of fluctuations in gravitational potential. It seems to be slightly smaller than 1, which indicates a preference for fluctuations on larger scales. What else? Tau is the optical depth of the universe, so the universe got re-ionized at some point, and so some 10% of the photons got scattered again. Actually, it's only 7.8 or 7.9%, if one is more accurate. And these error bars are, of course, correlated because they live in a 6-dimensional parameter space, and here 2-dimensional slices through this space. And showing what the data tells us. In green, you get the constraints from EE polarization alone. In gray, from TE. And in red, temperature. And the interesting thing is, polarization, which is a different quantity, tells us a consistent story in this 6-dimensional parameter space as temperature. Because when we treat these data sets separately, we have 2 independent measurements of cosmology, and they tell us a consistent story. It could have been that these ellipses are just apart. And of course, if you combine them, then the error bars get a bit smaller than the temperature. But I think the biggest value of this diagram is to see polarization and temperature do want the same thing. This is a standard grid in which we analyze the data. We can extend the parameter space by allowing some parameters which we usually have put to canonical values where we expect them, and also to allow to vary them. So what you see here is a helium fraction of the universe. Here you see a curvature in the power law by the slope of the fluctuations. And here you see the ratio of tensor to scalar perturbation. Tensor perturbations are gravitational waves, which also should have been excited during inflation, to these temperature fluctuations. The canonical values are shown at dashed lines, and at this moment we don't see any reason from the temperature polarization data for deviations of canonical values like curvature in the primordial spectrum, or presence of gravitational waves as they would have been printed on temperature. Not so much on polarization in this analysis. Other questions we can ask is the universe curved? Here is omega k, which should be 0 in a flat universe. And the data, if you combine the different data sets, really tell us, yes, it should be curved. Here's a different view on that. Omega lambda and omega meta plane. Let me go slowly. So if we take polarization data only, and with the polarization data we get this. If we add in lensing, we get a constraint here. And if we let BROs, we go to this point, which is on this dashed line, which is the location of universes which have omega total 1 and therefore are flat. So the universe seems to be remarkably flat. The inflation scenario was constructed in order to explain, among others, the flatness of the universe, and inflation is so effective in that one should expect that if inflation happens, that the universe should be indeed still flat today. And yes, that's what we find, so that's at least consistent. In this last diagram, here's another parameter, the sum of the neutrino masses. We can even measure this. The neutrinos are nearly as frequent in the universe as the photons of the C and B. So if they have mass, they should have changed the expansion history of the universe, and also they should have changed the growth of structure because they could transport significant amount of mass due to their mass. So they should imprint in the lensing effect. We can test the number of neutrino species because if there is larger than 3, there should have been more relativistic species in the early universe with an effect on the expansion history as well. And so far, we don't see any evidence for more than 3 neutrinos, or we have detected a significant amount of neutrino mass. This just illustrates where the neutrinos affect the spectrum, but since time is running, I want to come to talk a little bit more about the earliest time we can probe with Planck. Okay, so we see these structures here. These are growing modes of perturbation, of adiabatic perturbation, where matter and radiation, everything was compressed. But one could imagine different kinds of perturbation seeded at the early times. For example, perturbations where one species, for example radiation, is more enhanced at some location and less enhanced at another. But that matter is doing just the opposite, so that the curvature, that the density, the overall density, the sum of these two are the same. Therefore, the curvature is the same everywhere. So maybe some weird processes at the very early time, not inflation but some other, could have produced such initial conditions. And we can test for such so-called isocurvature modes, which we wouldn't expect in a standard inflation scenario, but which could be produced by other scenarios. And it turns out the data don't like them. So the data supports that these adiabatic modes, which are easily produced in inflation, and in particular the rising modes of them, are the ones which got excited. So if we assume we understand how the gravitational potential fluctuations in 3D are translated by all this radiative transfer and plasma physics process into the temperature map, we can try to invert this relation and try to infer with a little bit statistical knowledge we put into this about this fluctuation, try to invert this and to reconstruct the primordial gravitational and potential fluctuations on the sphere of last scattering in the vicinity of it. And here it is. So this is not the temperature map. This is from the temperature map reconstructed gravitational potential. And I think red means lower potential in this case. For color consistency reasons, red is now a value. There was a value here in the beginning of my talk, remember. If we add in polarization data, we get even more details of that. So we begin to reconstruct not only the photon field, but the gravitational potential which has imprinted on the photon field. And if we can do this, we can also measure the power spectrum of the fluctuation in Z. And that's shown here. Reconstructed power spectrum, here's a power, on logarithmic scale of k vectors. And the interesting thing is, over a large range where the data is very constraining, it's a straight power law. no kink, nothing, like with a lunar. As the simplest scenario of inflation predict such power loss. The simplest power law one could imagine would be flat in this diagram, but since inflation had to end, something has violated the scale invariance a little bit, and so this power law has a preference for large scales, as I told you before. This is an S parameter, and this preference for large structures can also be regarded basically as first confirmation of inflation theory. Just the data space here again. This is the CMB power spectrum multiplied with S squared, that you see better what's going on in small scales over here. And for a completely scale invariant spectrum, that would be the blue line. A slightly reddish spectrum which has no power on large scales is the red one, and the data clearly favors that. So you can see it darker. And one of the canonical predictions of the simplest inflation scenarios is indeed that this parameter is slightly smaller than 1. Not very much, but roughly of that order. So we are looking back into the earliest time when quantum effects shaped the universe, and when the universe was smaller as this grapefruit. Well, I'm just talking about the scenario where the universe expands. There's also a scenario, also born here in Heidelberg, where not the universe is expanding, but the matter is shrinking, from Christoph Wetterich. And even in that scenario, the statement is true that the complete visible universe would have been within that grapefruit, because grapefruits at that time would have been much larger, because they just shrank since then. Okay, so we're talking about the epoch of inflation. The scenario, the inflation scenario is that space was filled with a scalar field, and this had a potential, and it wanted to come down. So here's the field, the field equation. It's just something which is rolling down the gradient, but there's some friction. The friction is due to the fact that while if the universe is expanding rapidly, this is a Hubble constant, this is slowing down this fall down of the potential. And the Hubble constant itself depends to the Friedmann equation on the potential, on the energy density of the universe, and therefore on the potential. So if the potential is large, this Hubble constant is large, the friction term is large, and therefore this thing doesn't come down. And so the reason why it's up, why it can't go down fast, is maintained. If it's slow, therefore, you connect these terms, and we are in the regime of slow roll inflation, in which canonically the CMB data is analyzed. In order that it's really in this regime, some conditions have to be fulfilled. For example, the slope shouldn't be too steep, which is measured by the gradient of the potential in natural units, and as well as the curvature shouldn't be too large. So these two so-called slope or roll parameters should be small. But you see that once we know, if we would know what this potential would be of this hypothetical inflaton field, then we can calculate how it would come down and how the Hubble history, the expansion of the history of the universe would go. And if we add quantum effects to that, we can also calculate how fluctuations in the large scale fluctuations were seeded from which the large scale structure comes. So basically, we can translate a potential into a number of observables. And one observable is, for example, the amplitude of the scalar fluctuations, so the amount of fluctuations we see in the microwave background and later on with the large scale structure. Or the amount of fluctuations we should expect in gravitational waves, because also quantum effects in this inflationary epoch should have let the space-time shake a little bit, and these waves should have survived. If we take the ratio of these two quantities, we get the so-called tensor to scalar ratio, and by the mass of the theory, it turns out it's 16 times this small slow parameter. So this tensor to scalar ratio would, if you could measure it by measuring gravitational waves and scalar perturbations simultaneously and comparing them, would tell us directly about the slope of the potential in natural periods. And another way to look at the slope is, well, another way to measure this parameter is by looking at the spectral index, this NS quantity, which is slightly smaller than 1, and it should be if this parameter, which only can be positive, is dominating this equation. Okay. So, in Planck, we are looking at this primordial tilt and this NS and this tensor to scalar ratio. And from the temperature data alone, we can give you constraints which look like this. So, two large tensor to scalar ratios, in particular around 0.2, as it was announced by the collaboration, are not supported by the Planck data. In color, you see the predictions of a number of inflationary scenarios, and many of them are already started to get ruled out. There are a number of ones which survive, and in particular, one is this is down here, which is so-called R2 inflation. It's a modification of general relativity, which was the original scenario proposed by Stravinsky when he introduced inflation. So we are starting to constrain this inflation scenario. The real constraints might be a bit less tight than this one, because these were derived under certain assumptions. For example, that there are only 3 neutrino species, that the masses of the neutrinos are not that large. So if we would relax many of these assumptions, also these things widen. So if you preferred inflation model, it sits right here, don't give up hope, right? There could be other parameters which fix that. But we are starting to peek into the potential landscape of the inflaton potential. And here's an experiment where we try to reconstruct this potential from our data, or see what the data tells us about this potential. So potential as a function of field value. And each of these curves are a possible potential which is consistent with the data. So either the energy density was relatively low, but the potential was very flat, and the inflaton stayed here for a long time because there was not much of a gradient, or the energy density was high and there was a substantial gradient in the potential. Okay, so this is not very definite, but it's encouraging to get more information about the very first fractions of a second of the universe. And the last probe of this time epoch I want to talk about are gravitational waves. These waves should also have been excited in earlier times, and they traveled through the universe since then. And then when they came past this epoch of recombination, they imprinted themselves onto the CB by imprinting polarization on it. Okay, how should this work? Imagine you're standing here and a gravitational wave is pulling you like this. Whenever it pulls you upwards, and your plasma with photons in this, by the details of the complete scattering process, you get polarization aligned with the direction of stretching. A gravitational wave is something which moves in space, so actually you should think more about something coming like this towards you. So even in the third dimension, there's a correlated pattern of stretching and compressions. But actually the gravitational waves, which are primarily excited in inflation, should be circularly polarized. So actually it's a bit more like this. Okay? So circular varying pattern of stretching, which should imprint momentarily polarization pattern which also do these rotations. If now recombination cuts out some slice out of that and makes it visible to us, I hope you agree that it's at least plausible that a curly pattern of polarization are a result of that. Okay, so that's a short version of why gravitational waves from inflation should produce curly patterns in the polarization of the CMB. And such curly patterns have been reported by the BICEP team. And here's the curly pattern they found in the field is around the South Pole. That's a BICEP experiment at the South Pole. However, the problem is that our Milky Way has dust, and this dust also produces polarized emission. And this polarization orientation is here is in this pattern here. So the physical process is that the dust grains get aligned with the magnetic field of the galaxy, and then the emission is polarized. And the BICEP field, yeah, okay, this is the same again, just more beautiful. The BICEP field is down here in the region where there's not so much polarization of the galaxy, but nevertheless, here are the polar areas, the galactic poles. The BICEP field is here, and in color it is imprinted the amount of curly patterns, the so-called BMOs, in polarization imprinted by dust only. Okay, so this is a map of how large dust contaminates a search for curly patterns in the primordial field. And the result of this analysis is, yes, they picked a good spot on the sky. They could have picked a better spot on the sky. And the amount of curliness we expect from the dust is roughly as much curliness they have reported as potential gravitational waves. That seems to be bad news. The good news is we extrapolate from 350 gigahertz to 150 gigahertz, and of course dust physics is not rocket science, so there's a certain uncertainty involved in that, and this is roughly 25%, one signal. So it could well be that in their signal there is dust, yes, certainly, but there might also be some contamination by gravitational wave imprinted. How large it is, I can't tell you. The BICEP team and the Planck team are preparing, or actually have prepared, a common publication on that, which hopefully comes out in the very near future, which gives you the latest on that issue. Let me conclude. Planck provides us with an amazingly consistent cosmological picture. There are few things which are not really consistent, where small discrepancies exist, but I skipped over them for the sake of time. The Planck data supports the quantum fluctuation origin of cosmic structures and the inflationary scenario, while there might be other scenarios which explain the observation as well, but so far we don't know any which is as successful. In particular, the space is flat. We have found the radial fluctuation spectrum, and we see that there are growing adiabatic modes, and all these are prediction by inflation. We haven't found non-Gaussianity so far as inflation in the statistics of the fluctuations as inflation to some degree predicts. And we haven't found gravitational waves uniquely so far, but actually if the experts on inflation are actually not unhappy about this, because the amount of gravitational waves reported by the BICEP team made at least trouble for the simpler and more aesthetic inflation scenario. So the now available high precision and redundant cosmology data we have, CMB temperature, polarization, lens and galaxy surveys, permits us to perform precision cosmology and also precision particle physics, or Planck has confirmed the standard models of cosmology and particle physics so far. Let me thank you with showing the slide of the logos of all the institutions involved in Planck, just to remind you that several hundred people are involved in that and makes it possible. And it's an honor for me to be in the position to tell you these great results. Thank you. Sure. This? This feature? Yeah. It's not clear. Yeah. It's not clear. So this is one of the anomalies which seem to slightly violate our otherwise perfect picture of the universe. Things like this could happen by chance. So they're not extremely unlikely. They're unlikely, but they're not extremely unlikely. I also don't want to exclude completely that this is not a remaining systematics. So there are other features. If I go back to the 2013, you see, of course, also here it's not a perfect fit. In 2014, realizing the data, this got better. So we had another feature in 2013 at 1800. Here, you see this one. We found out that the cooling system produced a line in the data. So there's a certain, the cooling system has pumps, and this produced a line which imprinted onto the spectrum as its location. And so when we detected this effect, we could correct for it, and so the new data is free of that. Where we detected it, of course, in the timeline, where we have much more a better view on what the instrument does. So we have to stay tuned to what is happening there. We will reanalyze our data in the next year and update our understandings of the systematic effects of the instrument, and then we see if this remains or if this is a systematic effect. At the moment, is at the boundary of being three sigma effect. Okay, this is a part of the process.
Yeah, okay.
The higher order peaks, shouldn't they have a baryon loading effect also?
Pardon?
The higher order peaks in this, shouldn't they have a baryon loading effect as well?
I don't know, the height of the peak should have?
The higher order regular oscillations. So the first one, L equal to like 3220 is the first mode, yes. The higher order modes, the higher peaks, yes, these ones. We should have a baryon loading effect.
You can, in the ratio of these peaks, you can read off the baryon loading of the universe. So if the baryon density would have been different, the ratio of the even and odd peaks would have been changed. Is this your question?
Yeah.
The answer is yes.
So like in the second and third peaks, there should also be a difference, right? And the
as the later ones?
There is?
Yeah, sure.
Like how big is the rest of my
I don't know out of my head, sorry.
So what's the plan for the future now that the program is nearing?
Okay, for Planck, first we want to get our data and papers out. This hopefully happens this month. And then we will reanalyze the data for another year and have a final release in about a year's time. But that's not the end of CMB science. In temperature on the large scales, Planck basically has done it. On the smaller scales, there's a lot to do. The spectrum doesn't end here. If you look at it in a logarithmic scale and add in experimental data from South Pole Telescope and the Atacama Telescope, and then you see it continues, and there's still information to be gained. So Earth-based instrument will continue to measure the high part. In polarization, there more can be done. In case the Planck bicep analysis finds gravitational waves, this has to be confirmed. In case they don't, we should keep on hunting, because if inflation was correct, then there should be gravitational waves at some level. And so a number of missions targeting polarization, gravitational wave detection are proposed or in planning. One is a Japanese one, Lightbird. Another one is Core Plus, a proposal for a European mission. And yeah, that's... finally, the CMB also interacts with, for example, hot electrons in the galaxy clusters, leading to the Selyavich effect. And I'm pretty sure that this can also be used to study cosmology. So using the CMB as a backlight to illuminate a large-scale structure and extract information from that.
Okay, now discussion is free for everybody, so questions.
Can you comment on this frequency with the W map, data? Do you understand why there are more than 1 sigma?
So one discrepancy we had in 2014, in 2013 was this amplitude. And it turned out that 3 to 4 mistakes or things which we didn't know perfectly about instrument on our side led to a change which made us now consistent. So the discrepancy with this W map is not really large. Yeah. I think the largest discrepancy we have with Selyavich counts, so galaxy cluster, and there we are inconsistent with our own data actually. So our own catalog of Selyavich clusters with the cosmology fitted to their number statistics gives something which is on the 2 sigma discrepancy with ourselves. So there we have larger discrepancies. This W map discrepancy, I don't think it's that large.
Okay, other questions? Everything is clear? Inflation work? Yeah.
Could you comment on what's the largest improvement from the Planck, or what's the most important thing we've learned from the Planck that we didn't already know from the map?
Okay, I would say the confirmation of the quantum origin of the large-scale structure, that the tilt is indeed 0.96. Well, yes, we saw this in the WMAP data, but remember, WMAP also had a hint of non-Gaussianities, and this is gone after Planck. So not everything which is detected on a 2 sigma level survives. So for me personally, is precision confirmation of this simple lambda CDM model. One might be disappointed by that, but well, that's how it is. And that we have multiple ways to measure the same thing through gravitational lensing, through polarization, through temperature, and they tell us the same story. So it's on that level we seem to understand the universe, at least what kind of materials are inside. Also, we don't understand what these materials are.
Sorry, if P-mode polarization exists, how much they will change this result, or they will change or not?
If P-mode polarization would be detected?
Yes.
It depends on which level. I don't know how to answer this question. B-mode polarization would be detected, then we would have a confirmation of gravitational waves. So far, gravitational waves do not affect this data, are relatively independent of this data, although they have a small effect here on the larger scale, so they also imprint on the temperature data. So this would have a small shift for the cosmological parameter derived from this analysis, because then we know some part of this is modified by B modes. But I don't think that the cosmological parameters, which are mainly presented, are changed. What will change is our picture of inflation, because then we have to understand this level of B modes, is this consistent with which inflationary scenario, and what does this mean? So the biggest impact of detection of B mode would be our understanding of inflation.
So far you only showed low frequency data on the polarization, so what is wrong, or what is the issue with the high frequency data?
We still have systematics on the large scales in the high frequency polarization data. We can do null tests by subtracting one survey from another, and if everything is perfect and we see the same CMB in both, the remaining map should just show noise. If you do such tests, we see structures which are not noise, which are an indication of remaining systematics. For that reason, we have not used large-scale, high-frequency polarization data in this analysis, and we are also not going to release it at this moment, because there are obvious systematic effects in that, and they will spoil the analysis if we don't understand that.